Hi class, today we're going to start section 10.4, which is on the algebra of matrices. So first we're going to go over what it means for two matrices to be equal. The equality of matrices. Two matrices are equal if and only if they have, oops, oh, they got covered up. Okay. They have the same dimension, m by n, and corresponding entries are equal. And so that is every Aij entry equals Bij, where Aij is the entry corresponding to the ith row and jth column, similarly for B. So for an example, matrix, whoops, A, B, C, D equals 6, 7, 12, 1, if and only if A equals 6, B equals 7, C equals 12, and D equals 1. That's the only way these two matrices are equal. If A was to equal 3, then we know that these matrices wouldn't be equal. Okay, so now we're going to learn some basic algebraic operations, such as addition, subtraction, and scalar product of matrices. So if we let A equal the matrix with entries Iaj and B with the entries Bij, be matrices of the same dimension m by n, which remember is m rows and n columns. And we're going to let C be a real number. Okay, so 1, the sum A plus B is the m by n matrix obtained by adding corresponding entries of A and B. Second, the difference A minus B is the m by n matrix obtained by subtracting corresponding entries of B from A. So, oh, whoops, something I forgot to do up here. Come on. Was I forgot to write what the actual sum looks like for addition. So for addition, we'll have A plus B equals the matrix of Aij plus Bij. Sorry that I forgot to write that. So you add term by term. And then for subtracting, the matrix A minus B is the matrix of Aij minus Bij, where you subtract term by term. Okay. And then third, the scalar product, CA, is the M by N matrix obtained by multiplying each entry in A by C. So CA equals C times Aij for all the entries in A. So I know that this is all very abstract. So we're going to go through some examples. To really drive home the point and help you understand what's happening. So first, we're going to define a couple matrices. We're going to define A as 2, minus 3, 0, 5, 7, and negative 1/2. We're going to have B, B1, 0, negative 3, 1, 2, 2. And then we're going to have C equal 7, negative 3, 0, 0, 1, 5. And D equal 6, 0, negative 6, 8, 1, 9. So here are three of our matrices. So first, we're going to show A plus B. So here, we're going to write our matrices back out. Plus 1, 0, negative 3, 1, 2, 2. So here, we're going to look at these first entries and we're going to add them. Whoops. We're going to see that we have 2 plus 1. And then we're going to move on to the next one. We're going to do 3 plus 0, or negative 3 plus 0. And then 0 plus negative 3, which is us moving from here to here. And then we're going to do 5 plus 1. And then 7 plus 2. And finally, negative 1/2 plus 2. So we're going to take away a half, so that'll give us. And now, when we add all of these up, we end up with 3, negative 3, negative 3, 6, 9, and 3/2. So that's what A plus B is. And then we can look at C minus D, which is, if we look up back at C, it is 7 minus 3, 0, 0, 1, 5, minus D, which is 6, 0, negative 6, 819. So now, when doing our subtraction, we're going to do a similar thing. We're going to do 7 minus 6. Oops. 7 minus 6. And then we're going to do -3 minus 0. And then we're going to do 0 minus 6. And then we're going to do 0 minus 8. And then 1 minus 1. And then 5 minus 9. Now simplifying, we're going to end up with 7 minus 6 is 1, -3 minus 0 is -3, -6 is +6, 0 minus 8 is -8, 1 minus 1 is 0, and 5 minus 9 is -4. So this is our C minus D matrix. And then we can also look at what happens when we scale a matrix by a constant. So if we look at 5C, that's going to give us 5 times every entry in C. So that's 5 times 7, 5 times -3, 5 times 6, 5 times 0, 5 times 1, and 5 times 5. So then simplifying, we get 35 minus 15, 30, 0, 5, and 25. Okay, and then one last thing to keep in mind is if we wanted to try to see C plus A, if we were to write those out, C plus A, this would look like 7 minus 3, 0, 0, 1, 5. Oh wait, does C have a 0, not a 6? Did I write that wrong? I did, I'm sorry. Here, this should be 5. In my notes, it looked like a 6, not a 0. There we go. Okay. Plus, and then our A was 2, -3, 0, 5, 7, -1/2. So this, since they don't have the same dimension, when we start trying to add, we'll have 7 plus 2, -3 plus -3, and then 0 times. There's nothing here. This is empty. They don't have the same dimension. So C plus A is undefined. That's important. You need to have the same dimension to do these operations. Well, except for scaling. You can scale any type of dimension of matrix. Okay, and now we're going to move on to properties of addition and scalar multiplication. Of matrices. So we're going to let A, B, and C be M by N matrices. And we're going to let alpha and beta be real numbers, also just called scalars. Okay, so our first property is commutative. The commutative property of addition. So what this means is if we were to have A plus B, this equals B plus A. 2, we have the associative property of addition. So what this means is if we were to have A plus B plus C, that equals A plus B plus C. So it doesn't matter the order in which we add our matrices. We can kind of do it in any order and we'll still get out the same solution. 3. The associative property of scalar multiplication. So this means is if we had alpha times beta A, that's the same as alpha beta times A. So we can either scale the matrix by a scalar first and then a second one, or we can multiply those two scalars and scale the entirety of A by them. And the last one in this bit is the distributive property. Of scalar multiplication. So there's 2 for this one. So if we have alpha plus beta times A, that is alpha A plus beta A. We can split up the scalars like this. Also, if we have alpha times A plus B, that's the same as alpha A plus alpha B. So we can distribute our scalar in like this, or we can distribute 2 scalars out and we end up with the same thing. All right, so now we're going to look at an example. We're going to solve the matrix equation two x minus a equals b, where a is 2, 3, negative 5, 1, and b is 4, minus 1, 1, 3. So starting symbolically, if we have 2x minus a equals b, that we can add the a to both sides. So we get a 2x equals a plus b. And so now we can add what a plus b equals. We have 2x equals a plus b. Well, a plus b is 2, 3, minus 5, 1, plus 4, negative 1, 1, 3. And when you add those together, you get 2 plus 4, 3 plus negative 1, negative 5 plus 1, and 1 plus 3. And so this is 6, 2, negative 4, 4. And so this is what 2x equals. So now we need to divide by 2 on both sides, which is the same as multiplying by 1/2. So we have x equals, so when we divide all of these entries by 2, we end up with 3, 1, negative 2, 2. And then checking, if you were to do all of this in reverse, you'd end up with B. If you had 2 times this minus A, you'd have B. So there's our matrix equation. All right, and now I'm going to teach y'all matrix multiplication. So, multiplying matrices can be kind of tricky. So, first of all, AB, this is usually how we write multiplication of matrices. We just write them next to each other. Or sometimes A dot B, but very rarely. Of 2 matrices, A and B, is only defined when the number of columns in A equals the number of rows in B. So that means if we have A, which is an M by N matrix, times B, an N by K matrix, this inside term here, these need to equal each other. So the inside bit of the dimension, those have to be the same. So, and also, matrix multiplication is not like addition or subtraction. We're not going term by term and multiplying them. It's something a little bit different. So first, we're going to define the inner product. So if the dimensions of A and B satisfy the condition above, then if A, which equals A1, A2, all the way to AN, is a row of A, and little b, which is B1, B2, all the way to Bn, is a column of matrix B, the inner product of A and B, little a and little b, is the number A1, B1 plus A2, B2, all the way down to AN, BN. So, for example, oops. The inner product of 2, -1, 0, and 3, and 4, 0, 1, -2 is, so 2 times 4 plus -1 times 0 plus 0 times 1 plus 3 times -2, which is 8 plus 0 plus 0 minus 6, which equals 2. So now to actually get to what matrix multiplication is. So if our matrix A is an M by N matrix and Bij, is an N by K matrix, then their product, AB, is the M by K matrix C, which equals Cij, where little Cij is the inner product of the ith row of A and the jth column of B. So to kind of get an idea, if we had A times B, and we were looking at this row times this column, that would give us this block here, where this is the ith row, jth column, this is Cij. So to actually give you an example of what it looks like, sometimes in the abstract, it's very confusing. Once you start seeing it, it can be very helpful. We're going to let A equal 1, 3, negative 1, 0, and B equal negative 1, 5, 2, 0, 4, 7. So we want to calculate, if possible, AB and BA. So A is a 2 by 2, and B, actually, I'm going to write these underneath so I can demonstrate something better. So if we have A 2 by 2, and B, a 2 by 3, because remember it's number of rows, the number of columns. So if we look here, the inside matches. So these need to match for mult to be defined. But then what's important here on the outside terms, this 2 and the 3, that will be the dimension of the output. So since these two terms match, the 2 and the 3, A times B will give us a 2 by 3 matrix as its output. So now I'm going to write the matrices next to each other. 1, 3, negative 1, 0, negative 1, 5, 2, 0, 4, 7. Okay. And now the best way to matrix multiply, which is how I learned it here at Cal Poly, I had a now retired Bulgarian professor, Todor Todorov, and he would bark at us, "Oh, by Coulomb," in a very thick accent. But that's actually the best way to matrix multiply. We're going to multiply the rows by the columns. So if we start with row 1, we'll do 1, times -1 plus 3 times 0. So on our first bit, we're going to have 1 times -1 plus 3 times 0. So row 1 times column 1 will give us the row 1, column 1 entry. And then if we do 1 times 5 plus 3 times 4, we're going to end up with 1 times 5 plus 3 times 4. And now to get to our third column, we're going to do 1, oh, whoops, it's supposed to be a highlighter. We're going to do 1 times 2 and 3 times 7. So we have 1 times 2 plus 3 times 7. So multiplying again the row by the column. And now we're going to move on to the second row. So we're going to have 1 times -1 times -1, and then 0 times 0 again. So we have -1 times -1 plus 0 times 0. And now, oops, we're moving on to row 2 times column 2. So we're going to have a -1 times 5 plus 0 times 4. And then now for our row times column, we're going to have -1 times 2 plus 0 times 7. So now when we simplify all of these terms, we have a -1 plus 0, a 5 plus 12, a 2 plus 21, a 1 plus 0, a -5 plus 0, a -2 plus 0. So now simplifying again, we get -1, 17, 23, 1, -5, -2. And this is our answer. All right, and so now, and this is A times B. So now to look at B times A. So if we write those out, this was a 2 by 3 and A was a 2 by 2. Well, since 3 does not equal 2, we have BA is undefined. So this is also demonstrating that matrix multiplication is not commutative. We can't just pick the order willy-nilly. We have to be very, very precise in the way we're writing down the order of our matrices and multiplying them. So now we're going to move on to properties of matrix multiplication. So if we let A, B, and C be matrices for which the following products are defined, then first we have the associative property. So that means we can have A times B times C. This equals A times B times C. So this means that the order in which we multiply is not super strict, in the sense that we can't switch around the order, but we can do B times C and then multiply A on the left, or we can do A times B and then multiply C on the right. So we can pick like the orders within the, our set list and multiply them next to each other. And then 2, we have the distributive property. So that means we can have A times B plus C. This is AB plus AC. And notice that since A is on the left of the sum, that means it's going to be on the left of each of them independently. Okay, and then we also have A plus B times C. This is A times C plus B times C. So similarly, since C is on the right, C will be on the right of each of these terms. We don't want to reorder them because, warning, there we go. Matrix multiplication is not commutative. That means in general, AB does not equal BA. So for an example, if we take A equaling 5, 7, negative 3, 0, and B equaling 1, 2, 9, negative 1, then if we look at A times B first, this will give us 5, 7, negative 3, 0 times 1, 2, 9, negative 1, which is row 1 times column 1 is 5 plus 7 times 9 is 63. Row 1 column 2 is 10 plus negative 7. Okay, and then row 2 column 1 is negative 3 plus 0. And then row 2 column 2 is negative 6 plus 0, which simplifies to 68, 3, negative 3, negative 6. And now we're going to look at B times A, which is 1, 2, 9, negative 1 times 5, 7, negative 3, 0. And so now we have 1 times 5 plus 2 times negative 3 is 5 minus 6. And then we're going to have 1 times 7 plus 2 times 0. And we're going to have 5 times 9, which is 45. Then negative 1 times negative 3 is positive 3. And then 9 times 7 is 63 minus or plus 0, because negative 1 times 0 is 0. All right, and then simplifying this, we get negative 1, 7, 48, 63. And it's pretty clear to see because the entries are not the same. That AB does not equal BA. Okay, so this is the end of the section on matrix multiplication. I'm just going to stress again that when you are multiplying, you're going to multiply row by column. This is really important. All right, so that's where I'm going to end y'all today. Thanks.